Hi, everybody. So let's. Today's topic is that deep dive into PostgreSQL indexes. So we will discuss about the indexes in journal and how it works in PostgreSQL. So that's important that how it works in PostgreSQL because we are talking about the PostgreSQL. So in a general knowledge that we will learn the different indexes, how different indexes are worked and in PostgreSQL too. So my name is Ibrar Ahmed. So I have been in PostgreSQL since 2006, and I have authored multiple books on PostgreSQL. And here is the detail of my Twitter, Facebook, and LinkedIn profile. I'm now working in the Percona since last 3 years. So the timeline. So initially we will discuss about the heap and indexes. How heap, like table, and works in PostgreSQL, then about the indexes. Then we will go to the PostgreSQL indexes. We'll spend some time on PostgreSQL indexes. Then some useful queries about indexes. And then we will discuss the type of indexes available in PostgreSQL. Then some tips and tricks and some useful queries and different things we will discuss in 5 minutes. So here's a main picture of we were talking about the heap and indexes. So when we are talking about the heap, just imagine you have a book in your hand and you have to read the book. So it's like a heap in PostgreSQL, and in table, heap, it's the same thing. We will discuss that later. So when we are talking about the reading the book, we will read the whole book. So it's called a sequential read. Like if you are starting from chapter number 1 and you go from chapter number 1 to chapter number 10, 11, 13, and go on, then you are reading the book in a sequential order. So when you can check at the end of your book, you have an index where you can search any word and where that word is. So let's suppose here you can see in the left corner that the book, if you want to find the word buffer. So how you find that word in the book? You have to read the book fully from chapter number 1 to chapter number n to find where the word buffer is. So that's called a sequential scan. But it's just really difficult because searching of one word in a whole book is really tedious job. So, but when you see on the middle picture that you can see there is an index that pointed out that where the word buffer is. It will tell you the page number. So just keep in mind that index you have a pointer like this number, this name, the word have this page number, and you can go on that page and you can see the buffer word is there, a cache word is there. So you can search that word directly into the indexes. So you have to doing the 2 scans here. First, you have to read the index, the page number, then you have to go to the page number and you have to read the actual word. So in sequential scan, you have to read the full book to search the one word. But in indexes, you have to search the index, and index will point out to you to the book, and you have to read the book again, and you have to search that word. So just we have to keep in mind that the whole concept will be around this concept. So PostgreSQL tuples heap. So every table in PostgreSQL has a physical disk file. When you create a table, it will create a file for you, a separate file for you, for that table. So the physical file on a disk can be seen in PG data directory. PostgreSQL has its own data directory. Actually, it's called the environment variable PG data. So you can see that a whole cluster will be there in that data directory. So when you create a table, it will create a file for you in that directory. So tuple stored in table, when you insert some data into the table, then that tuple store the data into the physical files. And you have to keep in mind that these are not ordered. When you select from there, it's not necessary you will get the same order of the tuples, unless you have a order by clause on that. Otherwise, it's random. So if you insert some tuples and then you delete that and insert that again, so you will get a different order of that from that table. So here you can see that I just created an admin table with 3 columns and I'm just selecting from the catalog table, PG class, the name of that file. And you can see there's a like, should be the admin, it's not foo, it's just a typo, so it should be the admin. So you can see the file, rel file node, it's the name of the file. So it's 16384, and you can see in the data directory, the file exists in that directory. So I'm just giving you the concept, so how it works. So heap. So when we're talking about the heap, so when we are selecting the whole table, it will be a sequential scan. Like for example, you see, explain, analyze, select name from admin. So we are selecting all the names from a table. So it makes sense. You can see there is a sequential scan on admin. That means we are sequentially searching all the name in that table. So it makes sense if I say that just count the name of number of words in a book. So you will start from first chapter and you will go to end chapter or count the numbers. Or you can say you have to read the names from that book. So you are reading that book. So that makes sense. It's a sequential scan. You have to read the whole book. You have to scan the whole table. It makes sense. But in a second example, if you can see that we are searching a specific tuple where ID is equal to 1200. Does that make sense? Do we have to scan the whole table? So you can see, again, we have a sequential scan here. So we are scanning the whole table again just to search that ID is equal to 1200. That doesn't make sense. So why it doesn't make sense? Because we are searching just one tuple and you are reading the whole table just to find out that tuple. So, and you can see that here that we selected all the tuples, just filter out that ID is equal to 1200. So that doesn't make sense that we have a sequential scan here. So here, we are just in a sequential scan. I will give you the idea how sequential scan works in that PostgreSQL. Select static from admin where date is less than something like that, or just you can see all the values are there. So select CTID static from foo where ID is equal to 16. So as a CTID is a hidden column in a system column and a hidden column in PostgreSQL. We have not created that column when we are creating the table, but you can select that. So you can see the value, the physical storage of that tuple. So here you can see that CTID is equal to 1, 0. It means its page number. PostgreSQL store all the data in pages. So it's by default it's 8K pages. So first 1 is a page number and 0 is offset. So we have here, you can see that 1 is the page number and 0 is the offset. So let's see if we have a page or block. We can either say that the page or a block, we can say that. So we have a page, block, and 0, and you can see here 16. At 0, because it's a 0, it's 1, it's true, 0, 1, 2, and you can see the page number 1, at 0, we have a 16. So all the data stores like page number 0, page number 1, then page number 2, page number 3, it's like the data is stored in the 1 by 1 pages. So when you're selecting data, so like if you want to search for the ID is equal to 16, then you have to just go from here, you have to compare 1 is equal to 16, no. 10 is equal to 16, no. 3 is equal to 16, no. 16 is equal to 16, yes. So you're just returning that data. So you are sequentially scanning the whole pages, whole offsets, that where the value is equal to that. That's the problem. So it's, if you are thinking about it's time-consuming job, you have to compare each and every value. So here come the indexes here. Indexes are the entry point. Like sequential scan, we are scanning from the first chapter, first tuple to the end tuple. But indexes, there are the entry point. We jump to the direct to that tuple and return that value. So index used to locate the tuple in the table. So the sole purpose of the indexes are the performance. But the negative point is that it also holds some space. So like if similar, if you create an index, so it will create a physical file on the disk. So it will also consume space, but for the performance, it will give you the performance benefit. So here, you can see that we are selecting ID is equal to 1200, and then you can see the sequential scan, and you can see it's a time you can see in a millisecond. It's a red. So then you created an index, create index, IDX index on ID. So you can see you have created an index. Just check out the time difference. You can see the time is 2.56 millisecond now. Previously, you can see that the time is 26026.162 millisecond. So it's reduced the time significantly. Because previously, what we are doing, we were searching the value 1200 from each and every tuple. We are comparing that with the tuple. But now we are directly pointing to that tuple and returning that. That's why time reduced drastically. So now we're coming to the PostgreSQL indexes. So here, that's the same example that when we create an index in PostgreSQL, it will create a physical file. Like we have created a table that exists as a physical file. But when we are creating an index, it will also create a physical file. So it's almost the same thing. So you can search that file, the same PG class or like this, and you search that, and you can see that the file exists in the PG data directory, on the same directory where you have a table. So it's with a different name, it will create a file for you. So its syntax is always the same one, the create index, the name of the index on table and the column name. So we are creating a table, index on a table of the one column. So when you are using the index, just query that, you can see then explain that index is used or not. It's a simple thing that you are using the index. So creating an index is some kind of tedious job. Why? Because sometimes it's mostly lock the table. When you are creating an index, then you can't insert in that table or something like that. You cannot delete from that. So PostgreSQL have provided a way where it will not lock the table at that time. So it will slow down the process of creating an index, but it will give you the ease and you can manipulate that table in the meantime. So how do you do that? Normally you create an index on a table using something like that, create index. But if you put create index concurrently, then it will slow down the process of creating the index, but it will not lock the table. So you can manipulate that table at the same time while creating index on that. So that's important, that sometimes you require that when you are creating a table, it should not lock your system, the table. So you just put the concurrently. You see the time increase. Previously, it's a 12 second, look like a 12 second, and now it's 23 second now to creating the same index. It take more time, but it's not locked your table. So you can process, do any process on that table while creating a concurrent index on that. So expression index. So when you're creating an index, yes, when you just analyze in the PG stat statement and you know your application, that you are using some kind of expression while using some queries. Your queries have some expression, and you are always using that expression in your queries. So you can, instead of creating your index on a column, you can create an index on that expression. Like if you see that if you create an index on name, but mostly you are using a query where you have a lowercase name and you are comparing with some name. So when you create that index, using just name, it won't use because you are using the lore in that. So just create a index, like syntax is here. You can see that create index IDX name on admin lore. You can put the function name and the name. So you have created an index before, after applying the lore function on that variable or column. So it will store all the values of name in lowercase in that table, in that index, sorry. So when you compare that, it will give you the really good performance. So here on the left side, you can see that we are comparing David, and you can see that we have created an index on name. But when we are querying, we are using the lore. So that index won't used because we have not stored the value in lowercase. We are storing the case-sensitive value, not the case-insensitive. So in the right side, you can see that we created an index using the name lore, function lore. And that index is used, and you can see the time difference, the 1.157 and 71892. You can see the difference here. Here is some a little bit complex example of expression. Then you can create an index using the expression. Previously, we just used a lore function. Here, we just interval to days and dt plus. We have a bit complex expression here. So we will use that expression while creating an index. Because mostly when we are using our queries, we are using that expression in our queries. So when we're using that expression in our queries, then we create that index. So speed up our process here. So partial index, what is the partial index? Partial index is that if you want to save some space, like you have billions of records in your table, and you want to create an index on that, but you observe that you are not querying billions of records every time. You are just like, if not, you have a data like 1 year data, and you are only querying the current month data. Like you are always querying the January or February data. You are not querying the whole year data every time. So you just observe that. So you can create that index on that particular rows. You're not creating the index for the whole table. So it will give you the benefit, two benefits. First, it will create very quickly. Because if you create an index on whole 1 year data, that it's a process. It will take much more time. Secondly, it will require more space. But when you are specifying the where clause while creating an index, it will create an index for that particular rows for you, which satisfied that where condition. So when you specify the where clause, like here, create index IDs on bar. We are creating an index on a bar table with ID with no where clause. It will create an index on the whole table. And you can see the size 214 MB. And here, I just put create index IDX part on bar ID where ID is less than. So here we are creating an index where ID is less than 1,000. So you can see the total size is at 240 KB. Because we know that, we observed even in our application that we are usually querying where ID is less than 1,000. So why we are creating an index for where value is greater than 1,000? So we're creating an index, what data we actually require. So we create that index just for that value. But if your query is greater than ID greater than 1,000, then this index will not be used. Because we have not created an index for that data. We created an index for that particular rows, not for the whole table. That's the negative point, is that when we are querying outside of that boundary, so the index will not be used. But the size is lower when we are querying that within the boundary. That's called a partial index. It's not a full index, it's a partial index while you are providing the where clause in that. So index methods. So PostgreSQL have a different kind of method is PostgreSQL, like index, like btree, hash, gen, brin, gist. So it's have a different indexes here. So btree is the most common, is a index, and mostly people use that index. Because why? Because it works for the less than, equal to, less than equal to, greater than equal to, and equal to. So it's most of the operator we use, it works for that. And it works really good on that, is for that. So how you use that? Default is a B tree, but create index, name of the index on any table name, using, when you're using B tree, using hash, using gist, using gin, using brin. So you can use the name of that index. But if you don't use that, any using, so it will default will be the B tree. So here, when you are specifically creating a type of an index, you have to provide the using keyword with the name of that type of the index. So here, we just created an index, and a B tree index, so you just explain, analyze, so you can see the B tree index is used. So how B tree works? So how it's faster than the sequential scan? So you can see that here in the right side, you can see that it's a heap. We already discussed that, how we read that. Like if you want to find 12, how you find that in a heap? You have to compare ID 1 and 1, this values, all the value is 12. So return the tuple where value is equal to 12. So you have to compare one by one. So you have to scan the whole data. But here, when you created a B tree index, it will create a B tree for you. So how many hits you required? You can see 9. You can see is we are searching for the 12. 12 is in between 9 or 36. So we will go on the left side, and it is between 9 and 12. So we can on the left side is a 12. So it's only 3 comparison, and it will go directly to that tuple. That's B tree. Previously, how many hits we required? You can see that 1, 2, 3, 4, 5, 6. 9, 12. If we have a 12 record, then we need to have 12 hits to get to that tuple. But here we have only 3 comparison to reach to that tuple. So how we reach that tuple? Right now we have not reached that tuple. We have just identified the index value. So its index value is 12. Or you can see here the CTID is just slightly left, but it's 10. So you can see that at that value, you have that value and the CTID. We previously discussed what is the CTID. CTID is exact location of that tuple. So it will say at 1, and you can say a 0. At that position, every value has its own CTID. So we will read that from here, and then we will go to that heap again, and actually read the tuple. So first, we pointed out that the index will give you the CTID where the page number and the offset is there. Then we go to the heap, and at that page number and at that offset, we will read the actual value. So it's 2 read. One from the index to point it to the heap, we go to the heap and then read data from that heap. So here, I will give you the example. Another thing, that's called the index-only scan. So I told you in the last slide that when we are reading from the index, we are reading that from the index, we read the index and we get the CTID where we have a page number and the offset. So we read the page number, the offset, then we go to the heap again and read that actual tuple from the heap. So it's a 2 read, one from the index and one from the heap. But in PostgreSQL, there is a feature where we already have that full information into the index. We are not going to the heap. We're directly reading from the index. Like here, you see, create index IDX on foo. Simply created the index. And you can see I am selecting ID, name, and date from a table. So I required 3 columns from a table, but index is on 2 columns. Index on 1 column, like ID. But I am selecting here 3 columns. So I cannot get all the information from the index because index have only the IDs. It doesn't have the ID, name, and DT. So index only provide the pointer to the heap to me. So we have to go to the heap and read the rest of the information, name and DT. But when I select only the ID, and we know that we have already created an index using the ID, so we have the full information into the index. So we don't have to go to the heap to read the rest of the information. So we will directly return the information from the index. So I will give you the example here. So you can see that select ID from foo, where ID is equal to 74. So here you can see that we have a 3 hit, 69, 74, and then 74. And the leaf node, you can see we already have the 74. So we are just reading the 74. So we have enough information. We don't need the city ID here. We don't need to go to the heap to read the 74 because 74 is in the index. So we just return this 74. If we select ID comma name from foo, in that case, at 74 location, we don't have the name. We have only the ID here. So in that condition, we have to go to the CT ID and we have to read the name from there.
I have a question.
Yep.
Why is it in the explain, the cost why is it in the explain, the cost was exactly the same whether it was an index only scan?
In the last slide?
Yeah, yes.
Actually, it's not because, I have not a big table right there. So the table is small, so it's just reading that value. So it doesn't matter. But when you have a big table, so you can see the difference in that. So here, so when we are talking about when we have a full information in the index, we just return the value from the index. We are not reading from the heap. So the second one is the hash index. So just keep in mind the hash index only works for the equality operator. It's not work for the less than, equal to, greater than, equal to. It's just for the equality operator. So in hash, we have the name, you can see the name, and we have the hash key and the hashes and the TID. Previously, we have a B tree where we have the tree where we have a CTID. Here we have a hash key and then the CTID. So whenever somebody is like where ID is equal to 74 or something like that, whatever you want. So you see that we calculate the hash of that, then go to the hash, read the value from the CTID and go to that page number and read that value. Here, what is the hash index? Hash index only handles equality operator. I just talked about that. Hash function is used to locate the tuple. It just directly locate the tuple. So here you can see that create index using hash. I just word using hash. So you can see using hash is used and it directly reads tuple from the data. Brin index is a bit a new index. In that index, it saves the space of your index. If your data you have the correlation with this physical disk, location in the table, a physical disk, a location in the table has a correlation, then this index will work. Like if you have a data like a serial number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then it's physical correlation with the physical disk. If you have a data like January, February, March, April, May, June, July, it's relevant. What Brin index is doing, it's a block range index. It will create a block of ranges. If it's not a serial, it cannot create a ranges. Like if you have our data from January, February, March, April, May, June, July, August, so it will create a range for that. And it only stores the page number, the minimum value, and the maximum value. The index will store like from January to December, page number is 1. That's it. It will store only 3 values for whole data. So whenever you want to find data of March, it will just go to that page number and read that data. So if your data is a random, that Brin index cannot be used. So when you have a correlation, like serial number 1, 200, then 100 to 200, 200 to 300, then it will create ranges for you and save the page number and the range. Starting point, the ending point, and the page number. Starting point, the ending point, and the page number. So it will store that values. So whenever you query that, it will just check the range, in which range it occurs, and just return you the page number. So here, you can see that the date in a serial wise, and it created two ranges here. So you can see the sequential scan, the timing difference. I have created a sequential scan here. We have created a brain index here. You can see the timing. Timing a lot difference in the timing. But it's not only the timing difference, it's also the size. You can see the same data, the size of the B tree and size of the hash, and you can see the size of the brain index. It's just 48 KB. Otherwise, it's in MBs. Otherwise, here is a 48 KB. Size differences, because it's just stored the range. It's not storing the each and every value. It's just storing that from January to December, it's only just saving the page number. That's it. Generalized inverted index, it's a GIN index. It's handle the composite values. Actually, it's an inverted index. Like inverted index, like is 100% like. I will give you an example that in a book, end of the book, you have the indexes, where you can see the name, and you can see the posting list, full posting list. That this name occurs at 4 page, 5 page, 8 page, 10 page. So you can see the one word with a full posting list that this is in that pages. So it's 100% replica of the book indexes. So like here, if you create an index on the whole name column, because normally when you think about that, the equality operator, you are thinking about that equal to, less than, equal to, greater than, but it doesn't work in many cases. Where you, like text search, it doesn't work less than, equal to, something like that. You need some kind of an operator. You need some kind of index to point to the direct value. For the composite value, here you can see the JSON, where phone. So if I want to have an index where phone number is this match, how will I do that using the index on whole name column? I can't do that. So for this, here I have an example. Generalized inverted index. You can see that I have created an index on the name, and you can see the timing difference here. I'm just searching the name Alex. I'm just searching within that JSON document. So within the JSON document, I search that, and you can see the timing. So another, the gist, actually, it's generalized search tree. That's really important. That's like you have on a variables, like you are comparing that 10 is equal to 10, 10 is 8 is less than 10, 11 is greater than 10. So but in some cases, I just already described that it doesn't work with all the data types. Like points, we can't say that 1, 2 point is greater than 2, 4. Like points, this point is this point. Which point is greater? It doesn't like we can write a simple operator like this, or this point is greater than that. Or like something, this point occurs in this box or not. So it can't be handled using the greater than, less than operators. We have some kind of a mechanism that satisfied that kind of a condition. So I will give the example here. So here, I have a create table, a simple point. Okay, P point, I have added this point in that table. Like, you already know that what is a point. A point is just in a 2 dimension. You have the value here, that this point is X value and Y value. So you have a point here, 2, 2, 2, 4, 4, 2, 4, 4, and 4, 5, 5. You have, I just added some random value here. And what I did, I created a box. So I created a box where starting point is 2.2, ending point is 4.4. That's mean 2 here, 2 here, 2 here, 2 here. So I created a box. So I created a box table. I created a pointer table. So I just want to check this points table, which point is within that box. So I need to check that. So it can't be done using hash. It can't be done using B-tree. It can't be done using gen. It is only the option is gist. So here, you can say I have created a gist index on that, and you can see it will give index scan using IDX, it will scan, and it will return all the, P is less than B. That means which points in a simple points table are within that box I have created. So it will check each and every box, and it will return that rows. You got my point? That if we have this starting point 2, 2, 4, 4, we have this box. So we have a number of points here. So we will just pick one number and check, is this number within the box or not? Within the box or not? So we are just checking. So it will return all the columns. So it will return 2, 2, 2, 4, 4, 2, and 4, 4, because is it that in box. But it will not return 5, 5, because 5, 5 is outside the box. So this can't be done using other indexes. So we are directly pointing that to that value.
How does the index know that B without sequential scan is will lie?
Actually, when it's scanning, its mechanism, because it has a framework which we have implemented. I'm just talking about that in the previous. It's not just not a direct index. It's a framework where you implement that the whole logic there. So it's just a framework where you implement that, then it will store that value in that sequence. Then you can directly access that value.
What about floating point? If you have a decimal number, could you use a floating point number?
Yeah, actually, I said that it's a framework. You can implement that logic in that. It's not for the layman's, for the gist index. It's a bit difficult index. It's not like that, you just created that. If you want to have a floating point number, you have to implement that logic too. So normally B-tree index is used for mostly you use the B-tree index. 90% is B-tree index is used. A hash index is used only for the equality operator. And Brin is if you have a lineup data, so it's really good. Like the time series, something like that, you have a data, then Brin index is your guide. So gen used for the documents and arrays, gist is used for the full text search, or you can say the points in a box, something like that, so complex data types. So how much time we have? So we have 10 minutes, okay. So I think we have covered most of the indexes in PostgreSQL. So most of the time I have been asked that some useful queries that we have to write in PostgreSQL in the indexes side, that how we detect a duplicate index. What is a duplicate index and what is the drawback of duplicate index? When you create an index and sometime you forget that you have created an index on that table, and just a production system, you have tens of, 12s of indexes on that, you just created another index on that, which have the same index, you have created because you can create that. You just change the name of the index and you can create the same index. So what is the drawback of that? The major drawback is also consuming the space. Like if you have billions of record in your table and you have same billions of record in your index, but its column is less than that, but it requires space, and you have a same index on same column with just different names. So it's redundant. So how you detect that? Normally you can't detect it because the name are different. You are just searching, is IDX1, IDX2, 3, 4, name are different. But you have to see the name of the table. You have to see the column's name, that the columns are same. So sometimes you just forget that you have a duplicate index. So here is the query, where you can see that the Here, the index key 2 and AM name is a access method name actually, the B tree. So B tree, rel name, you have a duplicate index. I'm just selecting some rel name, index class, AM, index key. On second column, you have a duplicate index. So it will just give you that you have a duplicate index on that table with the column number 2, you have a duplicate index, just delete one of them. It's not going to give you which one is good and which was not good. No, it just gives you that you have a 2 index on the same column of the same table. Just drop one of them because it's no use. It doesn't matter which one you're dropping.
You know of any Postgres tool that will tell you at the time you try to add a duplicate that you're trying to add a duplicate?
No, when you are adding that, it's not going to give you the error. It will give you that just create it because the name is different, that's okay. For PostgreSQL, it's okay. So, it's just another query that support data types for a particular index. So, not every index supports the particular data type for particular data type. Like I told you that the point doesn't support that the B tree or hash. So this is the query. Sorry about that. You can get the slides. So it's quite small. That is quite a big list. So which GIN support this kind of operator and GIST provide this kind of operation. So if you just change the GIN, GIST, B tree, hash, so you can change the name here. Just GIN, GIST, you can put hash, B tree, BRIN, so it will give you the list. Which operator are supported, which data type are supported. So, there are 2 pgstat user indexes and pgstat statement you can use to get the statistics of the indexes. So, here is the query. Unused indexes. Sometimes you created an index, like you created one index, you created another index, you created another index, you are just creating the index on the table to get the performance. But sometimes it happens that your index never been used. How you detect that? Which index is used most frequently and which index is never been used? So why it's in this system if it's not been used? So this is the query. You just try this query. You can see index scan is a 0. The first one is a 0. That means it never been scanned, this index. So why it's been in the system? Just drop that index. Or just change the index to be used. So here, the other one, the 6, the 4, something like that. So you have a different kind of an index here. Okay. So, in Percona, we are hiring. If you are a database administrator, in a PostgreSQL, in a MySQL, in a MongoDB, then we are hiring here. So we have a booth here. You can have chat with me or a colleague, and you can go to the jobs.percona.com. So we are extensively hiring right now. So that's it. If you have any question.
Yeah, I don't know if it's implemented yet, and if it is, it's new, but is index skip scanning available? Can you speak on that at all?
Sorry, can you repeat?
Index skip scanning?
Index scanning?
Skip scanning.
Skip scanning, actually, it's going on, actually. It's not yet, David, yeah, I'm right. It's not right into the PG-14. The people are working on that.
Any other questions? We got a couple minutes left. All right, well, thank you so much. Oh, wait, one more.
Yep.
There you go.
When you're deciding whether or not to use a BRIN index, how do you know what the order of your tuples on the pages is to know if a BRIN index is appropriate?
Yeah, actually, it depends on your data. You know your data, actually. If you have a data like January, I always give you the example like January, February, March. If you have a data like that, first tuple is January, second is February, third is again January, so you can't use the BRIN index. It will create a BRIN index for you, but it will not give you the benefit. It will not hit that index. So you know your data, you are inserting data in serially, like January, February, March, April, you are adding data sequentially. It aligns with the physical days. But if you are inserting data like January, February, and again January, again December, and January, so print index will not be used. So you knows your data very well.
All right, I think last call. Great. Thank you so much.
Yeah, thank you.